Alright, here we go. So take home problem number 5. You start with a function, identified here in yellow, and you're asked, in A it says determine the intervals of increasing and decreasing behavior using interval notation. For me, I always start with identifying the domain of my function. And we'll get into that maybe a little bit later. But whatever you're doing with the function, if you're analyzing it, I think you should have a good handle on where that function lives. And if you look at this, you've got a rational function, right? We've got a polynomial in the numerator, polynomial in the denominator. It looks like if I let x be 0, I get -1 divided by 0, which is undefined. So 0 is not in the domain. So negative infinity to 0, union 0 to infinity. That's going to play a role later. Okay, knowing that this function is broken at x equals 0, that's going to show up. So anyways, we go to A, intervals of increasing and decreasing behavior. Well, if you want to know where a function increases and where it decreases, you want to know about its derivative, right? The derivative gives you instant access to whether a function is increasing somewhere or decreasing somewhere. And we're also going to work with critical points here. So in A, we need f prime. F prime of x equals, so what, you'd need the quotient rule and the power rule here. I'm just going to jump out to Wolfram alpha real quick and let it do it for me, because it's going to simplify it and make our life a little bit easier. And then also, if I show you how to input this in Wolfram, maybe we get some extra practice asking our T89 or your computer to help you with some of this work. So, oops, we'll go, we want Wolfram, O-L, there we go. So we're launching Wolfram in the browser here. Sorry, my PC's really thinking hard about this. Okay, so we wanted to ask Wolfram to do something for us. We said, would you calculate a derivative for us? So differentiate D8. This would be on your TI-89. You'd go F3, and it's the first option. So differentiate. We got to give it the function. So there's the open of the differentiate function. And what was it? X squared minus 1 over x cubed. So x squared minus 1, so the numerator, x to the second minus 1 over x to the third. We're going to differentiate with respect to x. And we'll say, tell us what you think. So thinking. Still thinking. Come on. Come on. So I might have to, we certainly could do it by hand, but there we go. Okay, so 3 minus x squared over x to the fourth. 3 minus x squared over x to the fourth. So we found a derivative. That's going to help us with increasing and decreasing behavior. As far as the intervals go, we're going to need our critical points. And so critical points, a point is a critical point if, well, I've probably oversimplified it for you here lately. I've said f prime of x equals 0. F prime of x is undefined. That's a little bit of an oversimplification. And the last quality here is that f of x exists. So, not a huge deal, but I'll show you how it plays out. So real quick, you want to know where your derivative is 0. and where your derivative is undefined. Well, if you notice, looking at your derivative is going to be undefined when x is 0. So you're thinking, oh, when x is 0, that's a critical point. Well, not so much, because when x is 0, your function itself is undefined. So do we care about x equals 0? Absolutely. You know, when we split up these intervals for increasing and decreasing behavior, we're going to have to make a split at x equals 0 because your function isn't defined there. But it would be inaccurate to say that at x equals 0 there's a critical point, and that's because this is a qualification for being a critical point. Your function exists there. So the only critical point we're going to have is going to be revealed when our derivative is 0. So I'll just ask Wolfram to tell me when the derivative is 0. So we'll just throw in a solve in front of this. Solve. Tell me when that thing there equals 0. Solve it for x. Oh, and I didn't spell solve correctly. S-O-L-V-E. So this is feeling a bit cumbersome right now, but we're going to get it. S-O-L-V-E. Alright, so there we go. This should do it. Solve. The derivative is 0 when x equals, and we could have just done this one by hand, I suppose. You know, if we go back, it says when's the derivative of that 0? It's at plus or minus 1.732. And that certainly would have been revealed if we would have solved this thing by hand. Now I don't want to go into too much detail here, but if this is your derivative, this fraction here, right? The only way you're going to get 0 out of a fraction is to get 0 in the numerator and not 0 in the denominator. So what makes the green thing 0? Well, plus or minus root 3. Does plus or minus root 3 make the denominator here 0? No, it doesn't. So f prime of x equals 0 when x equals plus or minus root 3. Equals plus or minus the square root of 3. So you have two critical points, right? When x is root 3 and when x is negative root 3. So the next thing to do would be to set up your intervals. So really you've got 3 separators for your intervals. You've got negative root 3, you have root 3, so you're wondering where the third is, and you have 0, right? 0 is going to be a separator because your function is undefined there. So if your function is undefined there, you're going to have to use that as one of those separators for describing when your function is increasing or decreasing. Because you don't want 0 to sit inside an interval, and you don't want to say that, hey, your function is increasing when x is 0. Well, because your function doesn't even exist when x is 0. So those are your separators. Okay? 2 of them are from critical points. 1 of them is from just your function being undefined somewhere. So let's look at our intervals. So f prime of x, so we'll write out the intervals. So we have negative infinity, if you don't know what the intervals are, negative infinity to negative root 3. We have negative root 3 to 0. We have 0 to root 3. And you have root 3 to infinity. So if you notice, like these divisions here, like these breaks in this interval, those are the only spots where your function is going to be able to change from increasing to decreasing. If a function moves from increasing to decreasing, a few things had to have happened. Either the derivative went to 0, the derivative went undefined, or the function itself went undefined. So that's how we know where to separate this thing. Because the only way a function is going to change from increasing to decreasing is if If its derivative goes to 0, derivative goes undefined, or function itself is undefined. So we have to describe what f is doing on each of these four intervals, whether it's increasing or decreasing. And our justification needs to be through the derivative. So I will say f prime of x is blank 0 on negative infinity to negative root 3. Therefore, f is, blank on the interval in question. So in here, we're going to put a sign, right? Like it's an inequality. It's going to be greater than 0 or less than 0. So we're going to do that for all four of those intervals. So I can copy this and just keep reusing it, copy it, paste it, paste, and then one more. Certainly have a lot going on here. Okay. So we're just about ready to start testing this thing out. If you can think about what I'm doing here is just getting ready to, I'm formatting my answer. Which right on this AP test, kind of sometimes you're going to know the right answer, but you're going to need to format it properly so that somebody can understand what they're reading. And there certainly are other ways to format it other than what I'm showing you here. But your justifications, you really need to be able to show somebody that you're making a decision based on calculus. And that's why in each of these you'll find that I'm talking about the derivative. Right? If you just said, hey, f is increasing because the graph of f shows me it's increasing, they're not going to reward you for that. So I'll just highlight this, clean it up. Okay. So really I have those four things to fill in. So this first interval in blue, okay, you need to take a number from that interval, any number, plug it into f prime, and see if you get a positive or a negative result. So, a number in this interval is, negative 10. So if you plug negative 10 into f prime, do you get a positive or negative result? Let's see, so 3 minus 100 over a positive result. So you get a negative over a positive. So f prime of x is less than 0. Therefore, f is decreasing. Next one, pick a number. I'm going to pick negative 1. So I plug negative 1 into f prime now. 3 minus 1 is 2, so you're going to get a positive result. And then the next one, pick a number in this interval, like let's say positive 1. Positive 1's in that interval. 3 minus 1 is 2. 2 over 1 is positive, greater than 0. You should go back and fill these in on negative infinity, negative root 3. This is negative root 3 to 0. This is 0 to root 3. And this is root 3 to infinity. Okay, and we had one more to go. We had this last interval. I don't know, number in it is 10. 10 into your derivative. 3 minus 100 is negative. Over a big positive is negative. So less than 0, which means f is decreasing. Okay, so you have answered the prompt for A. You have identified which intervals f is increasing on, which intervals f is decreasing on. And then B says any relative extrema. So relative extreme values, right, are just relative high points and relative low points. So I just, for B, relative extreme values, I notice my function starts out, okay, It starts out decreasing on this blue interval, and then on the next purple it goes to increasing, and on the next blue it goes to increasing, and on the next purple it goes to decreasing. So we've formed a relative minimum here and a relative maximum here. What happened at 0, really, well, your function couldn't have a relative min or max there anyways because your function is undefined there, but you end up having a vertical asymptote at x equals 0. So our relative extreme values, you think this is going to go on forever that way, this will go on forever that way. Oops. So our relative extreme values are at negative root 3 and at positive root 3. And just pay attention to how I justify it here. Right, so there's a few things. If you're going to argue that your function has a relative maximum, you're going to need to tell me that, hey, there's a maximum because coming into it you're increasing, going out of it you're decreasing. But also be sure to tell me that your function exists at that point. Right, so relative min at x equals negative root 3 because f of negative root 3 exists and f prime of x is less than 0 on negative infinity to negative root 3, and f prime of x is greater than 0 on negative root 3 to 0. And then we also have a relative max. See if I can save some time here. You got a relative max at, I'm looking back here, this should have been a positive root 3 right there. I don't know why I wrote negative. Clean that up. Positive, positive. And now I copied and pasted it a couple times here. So let's fix this one. I wrote it wrong there. This was root 3 to infinity. Hopefully I said it right. I think I just wrote it wrong. Okay, so we have a relative max at x equals positive root 3 because f of positive root 3 exists. And f prime of x is greater than 0 on f prime of x is greater than 0 on 0 to root 3. And f prime of x is less than 0 on root 3 to infinity. Cool. So there's B, your relative mins and maxes. So continuing on, we're going to go to intervals of concavity. So it's a lot like intervals of increasing and decreasing behavior. You're running the same test, you're just using the second derivative. So C, intervals of concavity. We need access to the second derivative. So the next thing I'm going to do is find the second derivative, and I can just jump right back out to Wolfram. C, okay, f double prime of x equals so I need the derivative of the derivative. So I'm going to get rid of this solve here. I'm going to change it to a differentiate. I no longer need the equals 0. So differentiate the derivative. So the derivative of the derivative. On your TI-89, you could have just, like, you'll do differentiate, put in your function, put in comma x, and then if you do comma 2, it'll do the second derivative. I tried doing that with Wolfram the other day, and it didn't like that format, so I did the derivative of the derivative just by putting differentiate within a differentiate. So there you go. 2 times the quantity x squared minus 6 over x to the 5th. So we'll go back and write that down. 2 quantity x squared minus 6 over x to the 5th. So when can your function change concavity? Well, let's see. Your function can change concavity if the second derivative goes to 0, or the second derivative is undefined, or f of x is undefined. So you're kind of going through this process, getting those interval separators. Okay, I know f of x is undefined when x equals 0. The first derivative was also undefined there. So that's going to be important, right? F of x is undefined when x equals 0. That's going to open up the door to a possible change in concavity. Doesn't mean it necessarily will happen. F double prime is undefined. Well, let's see. The second derivative is a rational function. You can't divide by 0. So f double prime is undefined when x is 0. So that one's kind of taken care of too. So you want to say like f double prime of x is undefined when x equals 0, but that's already been identified here. So still write it though. You want to convince the reader that you checked. Like, hey, I knew enough to look at where the second derivative was undefined. It just happens to be undefined at the same place my function is. So the last one, as far as these interval separators go for concavity, is where the second derivative is 0. So I'll just go back. I mean, you could do it here, I guess. So when is this thing? When is this thing? I'm going to highlight it in yellow. When is that 0? When x is plus or minus the square root of 6. So f double prime of x equals 0 when x equals plus or minus root 6. And you'll notice plus or minus root 6, neither of those values make the denominator 0. So if you wanted to compute it with the calculator, you just throw in the solve. So now we've got to write out our intervals, and then got to test some stuff. So I need a new page here. Okay, let's see if this will cooperate. I'm going to copy that because we're running out of room. And let's put it on the next page. Okay, so there we go. So our intervals. Let's see, you got negative infinity to negative root 6. We're going to have negative root 6 to 0, right, where your function's undefined. You'll have 0 to root 6, and you'll have root 6 to infinity. Okay, so now you just got to, you want to take numbers in those intervals, and you want to plug them into f double prime, right? The sign of f double prime is what tells you about concavity on f. So let's see. Let's saw a number in here. I'll just write. Okay, let's say negative 10 was our test for there. Negative 1, 1, and 10. So f double prime. So negative 10. Let's see, 100 minus 6, positive, positive. So f double prime is positive. Let's see, negative 1. We get a negative over a negative, that's positive. 1. We get a negative over a positive, that's negative. And at 10, we get a positive over a positive. Now the tricky part is going to be right here. You're going to probably want to try to call 0 an inflection point because concavity changed, but I get it, concavity is different on both sides of 0, but your function isn't defined at x equals 0, so 0 will not be an inflection point. It looks like our sign change happens right here, and I'm going to go back and double check this negative 10 real quick. Negative 10, yeah, that's a positive up top and a negative down below. Oh, so I did miss that. Negative 10. That'll just simple math there, right? See, I have 2 times negative 10 squared minus 6 over negative 10 to the 5th. That's going to give me a positive result over a negative result. So this should have been a minus right here. Okay. So we have the intervals of concavity. Now we just kind of got to put together our justifications. So I'll say, we can just list them out. F of x is concave down on negative infinity to negative root 6 because f double prime of x is less than 0 on negative infinity to negative root 6. Next, f of x is concave up on negative root 6 to 0 because f double prime of x is greater than 0 on negative root 6 to 0. I'm going to check that one real quick again. Let's see, negative 1 into f double prime. That was a negative divided by a negative, which was positive. Okay. Okay, next we got f of x is concave down on 0 to root 6 because f double prime of x is less than 0 on 0 to root 6. Almost done. One more. F of x is concave up on root 6 to infinity because f double prime of x is greater than 0 on root 6 to infinity. Okay, so you've described where this thing is concave up, concave down, and you've nailed the explanation there. So we go back up. There's one more prompt, and I think it was locate any points of inflection. So points of inflection means that a concavity changed, and you can draw the tangent line on your graph. So really, being able to draw a tangent line, there's a couple ways to think about it, but first off, your function better be defined there for you to be able to draw the tangent line. And secondly, except for a vertical tangent, the value of the derivative has to exist. So all I'm going to do is go down. I'm going to look at those intervals. Okay, almost there. Okay. Okay, D. Where did we change concavity? Okay, so negative root 6. Inflection points at x equals negative root 6 and x equals positive root 6. And first off, I'm going to say f of negative root 6 exists. f prime of negative root 6 exists, and f double prime of x. So this is now, I'm showing like you can draw the tangent. That was those first two statements, and now I want to show that concavity changed. And f double prime of x is less than 0 on negative infinity to negative root 6, and f double prime of x is greater than 0 on negative root 6 to 0. So those last two things, like this is really the statement that says concavity changed. The stuff right prior to that, that was just talking about being able to actually draw the tangent line on the graph. I got a little more. Also, f root 6 and an f prime of root 6 exist, and f double prime of x. Let's see, so at root 6 we said 0 to root 6 was, let's go back, negative and then positive, is less than 0 on 0 to root 6, and f double prime of x is greater than 0 on root 6 to infinity. We did it. We're all done. I'm really hoping that this video turns out, because that was 32 minutes. Oh.